Yo! Hey everybody, this is the video on scientific notation. So we're combining two sections into one because they're both pretty simple. So we're going to use scientific notation to represent very large and very small numbers. So no key terms here. So let's get to it. So what scientific notation is, you guys, is it is a way to write down an extremely large number or an extremely small number. We see scientific notation a lot in science and in different types of sciences. So like in biology, when we're talking about the size of an atom, and protons and neutrons, and electrons, they are all very, very, very small. Atoms are tiny. And so when we're talking about the size of it, we're using scientific notation to describe the size of an actual atom or all the parts of an atom. Okay, because that's the only way we can write down that super, super small number without having so many zeros that it's hard to count. Same thing with large numbers. When we're looking at astronomy for how distance apart that certain planets are or galaxies are, we're talking about things that are very, very, very far away, and we're using extremely large numbers. So we use scientific notation to represent those really large numbers. So scientific notation always looks like this. It's always going to be a number that is between 1 and 10. So it's got to be greater than 1 but less than 10. So greater than 1 or less than 10. So 1 point something, 2 point something, all the way up to 9 point something, but it can't be 10. And it can't be less than 1. So it's always going to be a number between 1 and 10 times 10 to a certain power. That certain power is like 8.4 times 10 to the fourth power is another way to write down the number 84,000. Now, I understand 84,000, not that difficult of a number to write down. It's not too large. But we're going to show you with these smaller numbers right now just to make it a little bit more simple. But we're talking about numbers that normally have like 20 to 30 zeros is when we really use scientific notation a lot. So 84,000 is 8.4 times 10 to the fourth in scientific notation. And if I were to figure out 10 to the fourth power, well, 10 to the fourth power is 10,000. I know that because that's how many zeros it represents. 1, 2, 3, 4. And if I were to do 10,000 times 8.4, it's going to give me 84,000. So this is a math problem that we're using to show as an actual number. So when we're writing large numbers in scientific notation, we're always using a positive exponent. Okay. And what we do is we always take our number and we move it. We always take a decimal that's at the end and we move it until we are left with a number between 1 and 10. And then when we do that, the amount of times we moved it, that's my exponent. So for 84,000, I moved my decimal over once, twice, 3, 4 times. So that's where 10 to the fourth power came from. And that's where I got to 8.4. So let's look at some examples here. 6,400, again, not a very large number. I understand that. But if I wanted to write it in scientific notation, we know that's 6,400, that's a decimal at the end. I would move it over once, twice, 3 times. Once, twice, 3 times. Because that's going to give me 6.4. 6.4 is a number between 1 and 10. And then that 6.4 is going to be times 10 to the, I moved it 3 times. So 10 to the third power. And I'm done. This is a different way to write this number. These both mean the same thing. Try this one on your own. Just try number 4. See how you do. Okay, so I got to move it over once, twice, 3, 4, 5, 6, 7, 8, 9, 10, 11 times. Because I have to end up here at 5.7. I'm sorry I missed, but it's going to be 5.7. And to do that, I had to move it 11 times. So that's 10 to the 11th power. That's it. So this is a big number, right? So an easier way to write this, there's not so many zeros. It's just 5.7 times 10 to the 11th. So for number 5, a light year is the distance that light travels in a year and is equivalent to this giant number right here. Write the distance in scientific notation. So again, we're going to start to the right. Count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I had to move it 12 times. I'm left with 9.461. It is okay to have more than one number after the decimal point because that's fine. This is still less than 10, and it's between 1 and 10, so that's okay. And I moved it 12 times. So that's times 10 to the 12th power. Now, if you're going from scientific notation to standard notation, it's the same process. The only difference is that you have to count this number, this exponent right here tells me how many times I have to move my decimal over. So because it's 7.034 times 10 to the 9th, I've got to move it over once, twice, 3 times, plus an additional 6, which is going to give me 6 zeros because I have to move it over 9 times. So that's 7034. I said 6 zeros because that's how many more times I have to go. And there's my number written out in standard notation where I'm no longer in scientific notation. This would be 7,034,000,000. Try number 9. So 10 to the 5th power means I got to move it over 5 times to the right. Let's find a different color. So I got to move it over once, twice, and then 3 more times to get to 5. So that means 3 zeros. So 2, 3, 6, and 3 zeros. 236,000. All right. And the mass of one roosting colony of monarch butterflies in Mexico was estimated at 5 times 10 to the 6th power in grams. Write the mass in standard notation 6 times. There's no decimal point here, so I just got to move it over 6 times. So I'm adding 6 zeros. So 1, 2, 3, 4, 5, 6. That's just 5 billion. 5 million, I'm sorry, 5 million. I think I said billion. And that would be grams. Okay, so this is for large quantities. For small numbers, everything's the same. We're just going in the opposite directions, and we're using negative exponents. So a negative exponent means we're representing a really, really, really small number. The reason why is if negative exponent, this is really 1 over 10 squared, which is really 1 over 100. So if I were to multiply this by 1 over 100, I'm going to make it smaller because I'm multiplying it by a number that's less than 1. So if I wanted to write a number in scientific notation, I know that this is a super small number, right? Because I have a decimal, it's a small number, so I know I have a negative exponent. And I have to move I know I'm going to end up at 8.29 because that's a number that's between 1 and 10. Same rules apply. And to get there, I had to move it over once, twice, 3, 4, 5 times. So it's times 10 to the negative 5th. So it's 8.29 times 10 to the negative 5th power. So the process is the exact same. I want to end up here at 3.02 because that's a number between 1 and 10. And I know it's a small number, so I have a negative exponent. And I had to move it over once, twice, thrice, 4, 5, 6, 7 times. So 10 to the negative 7th. Try this one. Typical red blood cell in human blood has a diameter of approximately that many meters. Write the diameter in scientific notation. So my decimal is going to end up here. So I'm going to have 7 times 10 to a negative exponent. And I moved over 1, 2, 3, 4, 5, 6 times. So it's negative 6. Same thing for going from scientific notation to standard notation. So now I want to go to standard notation. Because it's a negative exponent, I know I have to move to the left to make it a smaller number. So I just got to move to the left 6 times. So it's once plus 5 more to give me my 6 times. So it's going to be 5 zeros. And then 1, 0, 4, 5. Try 10 and 11. Okay, 9.9 times 10 to the negative 5th. Got to move it over once, plus 4 more, so that's 4 zeros. That's 0.000099. This one's easy. This is a silly one. 1 times 10 to the negative 2. This means I got to move it over twice. Once, twice. So this is 0.01. Okay. That's it, guys. So for things to remember, I don't really have anything to remember for you guys. So draw a house, please, so that you can get credit for your notes. So that way I know that you watched all of your, there's smoke coming out of the chimney. So I know that you watched all of your video, or the entire video. There's a cool window. I'll give it a second window. And then there's some grass. And as Bob Ross would say, let's put some happy trees over here with some happy clouds. Oh no, a line. That's a strike of lightning. I don't know how that made it lightning, but it works. All right, that's it. Hope this helped. If you guys have any questions, let me know. Rudy is out.